Good afternoon, everyone. Let's welcome our first speaker, Professor John Moreira from University of Warwick. He is going to talk on infinite sumsets on insets with positive density. Let's welcome.
So thank you. So my talk will be about two papers. So in the first of the two papers, the main theorem is the following. This was a paper joint with Florian Richter and Donald Robertson. And we proved that if I have a set of integers, or let's say set of natural numbers with positive density, so then I can find two sets, B and C, of integers such that they are both infinite and the sum set is contained in A. So I hope everyone has some idea of what upper density of a set is. The exact notion we need is upper Banach density, which is weaker. So if you don't know what there is, doesn't matter too much. We can even, the result is already non-trivial if we focus on sets whose density exists. So the density, when it exists, is just the limit of this proportion of the first n integers that are in A. So when the limit doesn't exist, we take a lim sup, and then we can take moving averages over different sequences of intervals, and that's how we get to upper Banach density. But that's not super relevant. So this theorem proved the conjecture of Erdős from the 80s. And then in this paper, we made a second conjecture, a stronger statement, which we then proved in our second paper. Maybe I should, just for historical accuracy. So this appeared on Archive in 2018. And then it took us 4 years to answer the stronger question. So this was a paper joint with Brian Akra and the same two authors, so Florian and Donald. So in 2022, these are archive dates. They were published a bit later. So we proved that in the same conditions, so if A has upper density, again, we just need upper Banach density, but the result is already interesting if we use natural density. So then, for any k, I can find infinite sets, not just two of them now, but k of them, whose sum set is contained entirely inside A. So for every k, so there exist sets B1, Bk, such that they are all infinite. And the sum set is inside A. Okay, so I hope the statements are clear. And so what I want to do is tell you a bit about how we prove these theorems. And so you may have noticed we are in the dynamics session, but these theorems are really about arithmetic Ramsey theory. But I promise the proofs involve quite a lot of ergodic theory, which is why I'm talking about them here. So before I talk about the proof, I want to say some words about why these theorems, some motivation why we care about this kind of things. So these fall into, as I said, arithmetic Ramsey theory. And so there are two types of results we consider in arithmetic Ramsey theory. There's coloring results and there's density results. So let me just do a small table here. So there's coloring results. So this means if n is finitely colored, some Ci contains something. Okay, and then we have density results which say that if A in N has positive density, then A contains some sort of structure. So these are the how statements in arithmetic Ramsey theory start in one of these two possibilities, and then the kind of things we care about. I mean, there's many ways to finish these sentences, but I'll just split them very broadly into two categories. So we can look for finite configurations or infinite configurations. And so just to give an example of a coloring result involving finite configurations, there's a famous theorem of van der Waerden, which says that I can finish this sentence with arbitrarily long arithmetic progressions. So I'll just put the name of the theorem here. So you may have heard of this. And there are many other results I can put here. There's Rado theorem, Schur's theorem. There's many ways to finish that sentence. Over here, on the density world, results are stronger and therefore harder. So there's few things I can put here, but there's a natural way to move this theorem over here. So if we keep our answer as arbitrarily long arithmetic progressions, then that's known over here. And this is a theorem due to Semeredi. And then when we move from finite to infinite configurations, a lot less is known, but there's still there's still some things I can put here in the coloring side. Maybe the most famous result here is a finite sums theorem of Heinemann. So there's some other things, Millikan-Taylor, I could put over there. But then over here, there was nothing until our first theorem there. So there was no density result that involved infinite configurations. You could make some trivial counterexamples to what I just said. So there's some maybe artificial infinite things you could put here, but in general, there were no natural statements like these three. So again, in density sets that involved an infinite configuration. So this was the first result in 2018. This was the second result in 2022. And the proofs we came up with have really been applied now to many other problems. So I did a quick count. There's now 13 papers on arXiv to this moment that fill in configurations to put in here. So this has really started, I think, a new way to, again, fill in answers in this final box of this table. So that's why we care about this sort of results. So let me then explain how we prove this, or rather how ergodic theory appears in the proofs of these theorems, because, again, there's no ergodic theory yet. And the reason to even expect ergodic theory to appear there is because of the work of Furstenberg, who gave an ergodic theoretic proof famously to the theorem of Semeredi I mentioned over there. So let me maybe make a precise formulation of Semeredi's theorem, first of all. Semeredi. So this was proved in 1975. It just says that if A has positive density, then for any length k, there exists some nm such that the arithmetic progression is inside A. And so Furstenberg looked at this theorem and he said, this is an ergodic theoretic statement, which of course it isn't, but what he did more precisely, he proved the following multiple recurrence theorem. Furstenberg. So this was 2 years later. Okay, so let me state the theorem. Let x mu t be a measure preserving system. So I hope I don't have to define this. So this means I have a probability space here. X is a probability, well, X is a set, mu is a probability measure on X. And then T is a map from X to itself that preserves that measure. That's why it's a measure preserving system. And then let E be a set in X with positive measure. So then for any K, there exists some time n such that the set E recurs after time n, and then again after time 2n, and so on. So Furstenberg proved this multiple recurrence theorem using ergodic theoretic terms. That's in a way not surprising because this is definitely an ergodic theoretic statement. But what I want to show right now is how he used this ergodic theoretic statement to prove Semeredi's theorem. So they're actually equivalent. There's easy ways to go in both directions, but I will just prove the direction we are interested in. So how does ergodic theory can be used to prove Ramsey theoretic statement? So proof of Semeredi's theorem. Okay, so I start with a set of positive density. That's the only ingredient, well, and the K. But the K will come in later. So let A be a set of positive density. So now in order to use multiple recurrence theorem, I need to find a measure preserving system. And so we start the construction of this system by just looking at the full shift on two symbols. So this is a dynamical system. I'll call it x0. So all, let's say, by infinite sequences on 0 and 1. And t is just the left shift. This is called the full shift. And then the reason I brought this up is that I need to use my set A somehow. It needs to be visible in this system. But I can look at the indicator function of A. This will be a sequence of zeros and ones. And therefore, it will be a point inside my space x0. Okay. So let A in x0 be the indicator function of the set capital A. So more precisely, given by A n is 1, if and only if n is in capital A. And so now I can take the orbit closure of this point to be my set X. So this will be a set which is invariant under T. And the last thing I need is my probability measure, which should be invariant under T. And so what I will do, I will take the empirical measure at the point A. So I'll take here the limit as n goes to infinity of these averages of the Dirac masses at the orbit of A. Now I'm lying a little bit here because limits don't always exist. When limits don't exist, because the space of measures is compact in the weak star topology, we can take a subsequence. But let's ignore the details. Let's just assume the limit does exist. So there are technicalities that can be that we may need to consider, but let's ignore them. And so now we have here a measure preserving system. So there's space X, there's the T, it's just a left shift, and that's the invariant measure. It's also easy to show the measure is invariant. So I still need to define the set E that I will apply the theorem to. So final ingredient, E, I will take the cylinder set at 0. So I'll just describe it. So the set of all sequences in X whose 0th coordinate is equal to 1. And then because of the way I defined the measure, we can see that mu of E is exactly the density of A which is assumed to be positive. So I can hit this data with the multiple recurrence theorem, and we conclude that, okay, so we conclude that this thing happens, which then implies that okay, so the density of A minus n up to A minus kn is positive. And then if I just take any number m in there, I will find my arithmetic progression in A. Okay, so I don't spend too much time here, but we are essentially done at this point. So, so this is how we can go from an ergodic theoretic statement, like the multiple recurrence, to an Ramsey theoretic statement, like Summered's theorem. And so that's why we hoped to, so when we first were working on this paper, we hoped maybe we can use ergodic theory to attack this problem. But very early on, we realized there were issues with this idea. So, so maybe I can even do it here. So note that I can rewrite this condition, B plus C being contained inside A. This is equivalent of saying that B is contained in the intersection of all these shifts of A given by elements in C. So that's just a set theoretic rewriting of that inclusion. And so if I wanted to use a similar method, I would hope that this, to show that this intersection is infinite by showing maybe that it has positive density. But that's an infinite intersection, and so it's very unlikely it will have positive density, and in the measurable case, there's no way I can hope for intersecting infinitely many translates of a set E and have positive measure. For instance, if the system is mixing of all orders, that's definitely not going to happen. So there's no hope to just use the exact same correspondence principle of Furstenberg. But so then what we can notice is in this construction, this is, by the way, Furstenberg's original construction, well, roughly. So there's some data here we didn't use. So for instance, we can recover the set A entirely from this dynamical data. A is the set of times that my point little a visits my cylinder set E. And this makes sense because E is a Klopen set. So it's not, if it's just a measurable set, I could change it in a set of measures 0, and I wouldn't notice the difference. But E is a Klopen set, and so, I mean, yeah. So we can recover the set A from the data in this system. The problem is that we now need to pay attention to this point. So this is now a special point in my system. And so if I want to translate the combinatorial statement to a dynamical statement, I won't be able to have something as clean as Furstenberg that handles measure-preserving systems. There's no topology in this statement, and there's no points in this statement. There's just sets. For us, this will not be possible. I need to pay attention to this special point, and I need to pay attention to the fact that this set is nice. It's Klopen. Klopen means, by the way, closed and open. Okay, so how do we go forward? Let me erase something. Yeah, so actually here we can already do a statement. So I will erase this theorem. We'll come back to this one later. Okay, so we can already formulate a dynamical theorem that implies this theorem. So So let x mu t be a measure preserving system. But now I need some topological information. I will need that T is continuous. In fact, I want it to be a homeomorphism. And so I need X to be a compact metric space. So I don't want to write everything down. But so we need some topological information about our system. Fine. And then I need my special point. And so what's so special about this point A? A was used over here to define the measure. The measure mu that I use is the empirical measure at A. And so when this happens, we say that A, because it generates the measure, we say that A is a generic point. So let me just write that here. So this formula here, when this happens, I say that A is generic. Okay, so let A be generic, so satisfy that yellow box. And what else do we need? We need a Clopen set. Let E be Clopen with positive measure. Okay, so we need a little bit more data than Furstenberg needed here, but now we can finish the statement. Then, then there exist infinite sets B and C in N. And B plus C is contained in the set of times N such that TNA is in E. So arguably there is a statement in ergodic theory, but it's hiding really the difficulty, because I still need at the end of the day to find two infinite sets whose sum is inside some dynamically constructed set, but still some large set. So we didn't really do much, we didn't advance much our understanding of the problem by translating it in this way. So it's not quite as nice a picture as what Furstenberg had here. In our first paper, however, this is as far as we got into translating the paper into dynamics. So what has happened in this area is that every new paper we write, we prove a stronger theorem, and the proof is easier, because we understand better how to encode things dynamically. So in the first paper, this is as far as we got, and then to prove this statement, we had to work very hard. We actually didn't even formulate this statement because it doesn't really help. We just proved it directly. So, so let me tell you what, let me tell you one special case. So there's one case of this theorem we can prove right away, and this was actually useful. That's when the system is weakly mixing. So let me erase, tell you how we do that. So in ergodic theory, or at least in ergodic Ramsey theory, when we use ergodic theory to look at Ramsey theoretic statements, we often have to consider different cases separately. So when the system we want to analyze is mixing, or when it's structured in some ways, and then hopefully put the two behaviors together. And so weak mixing is a natural assumption. So let me give a cheeky definition. Measure preserving system is weak mixing. I should spell it out. If for any two sets, I'll use A and B, not good, E and F in X. So what does it mean? want to consider this sort of intersections. I want to apply the dynamics to one of the sets and see how it intersects with the second set. And a system is mixing if there is asymptotic independence between sets. So I want to say that asymptotically, translating this set E will land somewhere which is independent from F. So I want to compare this measure with the product of the measures of E and F. And so I will give myself an epsilon, and then I want to say that this is most of the time smaller than epsilon, in the sense that the set of times when this is bigger than epsilon should have zero density. Let me flip. So the set of times when this is smaller than epsilon has full density. Okay, so this is not exactly how weak mixing is usually defined, but it's equivalent to the usual definition. And so let me prove, I didn't give a name to this theorem, I think it's maybe theorem 6. So let's proof of theorem 6 for weak mixing systems. Okay, so this is a very special case, but this proof really explains how a dynamical argument can be helpful in understanding, in constructing these sumsets. Okay, so we have this data, we have some dynamical system. Okay, some generic point, some Kloppen set, fine. But the point is we want to find B and C. That's all we want to find. And so B and C, I can enumerate these sets. In fact, I should have done this already. So B, let's call it B1, B2, B3, okay. Same thing with C. So I want to construct really two sequences, B's and C's, such that the sum is always inside the visit times. And so I can pick any B1 that I want, it doesn't matter. Arbitrary. And then I want to pick C1 so that the sum is inside the set I care about. So take C1 just such that T C1 of A is in T minus B1 of E. So why can I do this? So E is a set which is Kloppen and has positive measure. So when I take any pre-image of E, it will still be Kloppen, T is continuous, and have positive measure, because T preserves the measure. And A is a generic point. So generic point will always enter a Kloppen set with positive measure. So I can always find such C1, and when I do, C1 plus B1 is in the set of visit times 2E. Okay. So this was easy. Okay, now to pick B2, I need to be a bit more careful. So I want to make sure when picking B2 that I will be able to pick C2 in a moment. So I want to pick B2 such that, well, first of all, I need T B2 of A to be in T minus C1 of E to guarantee that the sum of B2 and C1 will be in my goal set. But I also need that these two pre-images of E intersect with positive measure. So why can I choose such a point B2? I need to look at the set of all elements that satisfy the second condition. And because of my weak mixing assumption, I know that the set of B2s that satisfy this condition has full density. So there's a full density set of choices that satisfy the second condition. And Okay, there's a positive density set of choices that satisfy the first condition. Again, that's because this has positive measure and A is generic. So there is going to be some choice that satisfies both conditions, and that's my B2. Okay, I think this is the most important step of the proof, so if there are any questions here. Okay, so I will write one more line, but I could say and so on. Well, I'll write one more line, just so then we pick C2 such that T C2 of A, it needs to be in T minus B1 of E, and it also needs to be in T minus B2 of E. That's why I needed that to have positive measure. And to make sure I can continue, I also need that measure T minus C1 of E and T minus C2 of E have positive measure so that I can choose B3 in the next line. Okay. Okay, so I think so I can keep choosing B's and C's forever, so this will produce two infinite sequences satisfying this conclusion. Okay. Okay, so for weak mixing systems, even this bad dynamical statement is easy to prove. Well, easy-ish. So we need to focus on the systems that are not weak mixing. And so this has been known for a long time that a system is not weak mixing if and only if it has some measurable eigenfunctions for the Koopman operator, or in other words, if it has a factor map to a rotation on a compact abelian group. So in particular, what if the system itself is a rotation on a compact abelian group? And here we need to be careful. If the system is topologically conjugate to a rotation on a compact abelian group, then we can use algebra to solve the problem. This is not so difficult. But we are now in the realm of ergodic theory and measurable maps. If the system is measurably isomorphic to a rotation on a compact abelian group, we already don't know what to do. Why? This problem is very sensitive to this point A. And if I have a measurable isomorphism, I completely lose track of what is happening to A. A may disappear. Okay. So this is where our troubles began. But it's a measurable eigenfunction. So A, yeah, the value at A, I can change it. So yeah, so I won't tell you how we handled that issue because it wasn't the best way. 1 year after our paper came out, Bernard Host, he gave another proof of this theorem where he explained better how to handle this situation. So, so here's what he showed. So Host showed that, well, this maybe he used, I think he knew this already from an earlier paper. Okay, so he used the fact, I should say it before I write anything down, that we can always pass to an extension of X such that the factor map to the Kronecker factor to this group rotation is actually continuous. And this is a non-trivial statement because, okay, we need to keep track of this generic point A. So this is a delicate point, but I want to just say, so use the fact that after passing to an extension, we can assume that the factor map to the Kronecker factor, this is the maximal group rotation, maximal group rotation factor, is continuous. Okay, so this was something we didn't know about, and it really simplifies the proof somewhat, because now we can make use of this fact that the system is either weak mixing or it has some group rotation factor with a continuous factor map that we can then somehow use. So this doesn't solve the problem, but it is a step in simplifying the rest of the proof. So, yeah, so this is a continuous, extension of, yes. And the extension is measure theoretically isomorphic. So we don't add any measurable eigenfunctions, but we add enough continuous eigenfunctions to. So yeah, maybe I will skip this part. Okay. So I have 20 minutes. Okay, so maybe this is enough about the first paper. I'll now move to the second paper. Okay, so we needed a somewhat different viewpoint. So Host has a slightly better dynamical theorem, but it's still, I mean, I wrote it down there. I wanted to write it here, but it would take 2 blackboards, and it's still not very clear why that is helping us. And so we wanted to understand better the underlying dynamics. So we went back to the drawing board when we started working with Brina to try to understand what's happening here. So how do we prove that dynamical theorem, but what's going on there? And these ingredients, so this was very important to what followed. So let's keep it up there. Okay, so suppose, well, we had the theorem at this point. We knew this was a true statement. So we do have these 2 sequences, B's and C's. So let's see what happens when we apply these sequences to the point A. So first observation, after passing to a subsequence, I can assume that, so I want to say B plus C is indeed contained in this set. Okay, and let X be the limit. Again, it will exist after I pass to a subsequence of TBN A. Now, every time I apply a Cm to this point, this will always be inside the set E for every M. Why? Because this will be the limit of a sequence of points that are in E, and E is closed. And so in particular, if I now let Z be the limit as M goes to infinity of T, C, M of X, this is also in E. So let me draw a small schematic figure of what's happening here. So I apply T to the power Bn. I am at this point X. And then I apply T to the Cm, and I am at this point Z. And Z must be inside this Klopen set E. But I can now reverse the order I did things. I can take a point Y, which is the limit of T Cm of A, and then I can take, let's call it Z tilde, to be the result of applying T Bn of Y. So what I do now, I apply the T to the Cm sequence, and I call this limit Y, and then I apply the T to the Bm sequence, and I'm again in a different point z tilde, but it's also inside E. Okay, so why am I doing all this? It turns out that if I have this picture, if I find two sequences Bn and Cn where the limits are inside E, I can then pass to a subsequence of both Bn and Cn which satisfy the conclusion of the theorem. So this is a half a page argument or chasing subsequences. And the advantage is that now I don't need to care about the entire sequence. I just need to care about these limit points, both being inside E. So this was the first observation in the second paper. But in the second paper, I already raised the statement, but you will remember, we don't just end up with the sums of two sets B and C. We wanted, say, three sets, B, C, and D, which would lead to three sequences, Bn, Cn, and Dn, which would lead to 6 orders in which to apply these limits. So we had 6 points we wanted inside E. And this was a headache. And we were taking aspirin for a year, but the headache didn't go away. So then we made a revolutionary decision. We decided to be overly optimistic, unreasonably optimistic, and say, what if instead of showing that we have 6 points that are all inside E, what if instead we have a single point that all those limits agree to, and that point is inside E? And this was ridiculous, but turns out this was true. And this is what we ended up proving. Okay, so let me make a definition, and then I will state the new result. So maybe here. So I'll do it for just 2 summons, but then, yeah, then you can extend to more. And so we call these objects because these all started in connection to a problem by Erdős. We call these things Erdős squares. Okay, so let Xt be a topological dynamical system. So I don't even have a measure right now. Then a point a x, y, z in x to the 4 is an Erdős square if there exist sequences Bn, Cn, and I need them to be injective or increasing, such that, and so I need that the limit, okay, all the 4 limits over there. So T Bn of A is x. Let me write it like this. T Cn of x goes to z. T Cn of A goes to y. And T Bn of y also goes to z. So, well, it's essentially the picture over here, but with z equal to z tilde. And so the theorem now, already with Breine, Florian and Donald, was that under these assumptions, I didn't want to write everything again, but let x mu t a e as before. Okay. So I mean everything up to this point. Then there exists an Erdős square A, X, Y, Z with Z in E. Okay. And so this is the dynamical theorem that we ended up with that implies the combinatorial theorem up there. And so a similar theorem, well, first of all, a similar definition can be made for higher dimensional cubes, where you have more sequences and more points, but then all the points coincide when it's reasonable to expect so. So maybe I think I'll skip the definition. And then we have the exact same statement, so for any dimension. Now, a small caveat is that this theorem is not equivalent to that. So the combinatorial theorem does not quite imply this, or at least we weren't able to derive this from that. What that theorem gives us is precisely this picture, where Z and Z tilde may be different. They are both in E, so they are both very close to each other, but potentially different. So the dynamical theorem in this case is strictly stronger than the combinatorial theorem. Okay, so let me make sure I didn't skip anything important. Yeah, okay. So let me say just a little bit about how we prove this. So the proof goes into parts, really. So first, we need to understand just these objects, Erdős squares, in general. So where do they live, how we can control them, find them. And then we need to make sure that there are plenty of Erdős squares whose last coordinate is in E. That turns out to be easy. The harder part is to make sure we have an Erdős square whose first coordinate is this point A we started with. We cannot run away from this point A. And this, of course, is a zero measure set of squares. So, okay, so let me say just a little bit about the first part, and then I'll explain in 2 minutes how we isolate A. Okay, maybe example. So when X mu T is weak mixing, then so mu cross mu is ergodic, is a measure on the product space. And then if I take the fourfold product, so this is a measure on X to the 4, mu cross mu cross mu cross mu, almost every point in X to the 4 is an Erdős square. So I don't have time now to prove this, but it's really not very difficult proof. Yeah, using the fact that mu cross mu is ergodic for T cross T. And in general, I think I can define here. And so in general, we can describe very explicitly a measure on X to the 4 with the property that almost every point with respect to that measure is an Erdős square. Okay, so in general, if mu cross mu is not ergodic, so if the system is not weak mixing, mu cross mu is not ergodic, so it has an ergodic decomposition. Let's say nu sub y d rho of y, some space of ergodic components. We let lambda be the integral over rho of just nu sub y times nu sub y. Y d rho little y. So we extract the ergodic components of mu cross mu, and we just pair them diagonally. And okay. So it turns out that lambda almost every point is an Erdős square. And the proof of this in our paper is very simple, but this is because it turns out that this measure was already considered, well, this measure maybe even by Furstenberg, but surely by Host and Kra in 2005 when they were studying in connection with Furstenberg's proof of Semeredis theorem. They were studying convergence of non-conventional ergodic averages. And in this work, they had to develop some cubic measures, which in the case of two-dimensional cubes coincide precisely with this measure. And so they studied lots of properties of these measures. So again, this is only for two-dimensional squares, but we define this for any dimension. And so they already had all the properties that we needed, almost by magic, in their paper. So you were able to just use the work they had done to understand these measures, to then understand our Erdős squares and higher dimensional Erdős cubes. So this was really very lucky of us. We would not have been able to do this if we were working before 2005. So I won't prove that the statement that lambda almost every point is an Erdős square. In fact, I will not prove much more. But so let me just roughly explain how we use this measure to finish the proof of the theorem. So an observation is that when I project this measure lambda to the very last coordinate, so this is a measure on x to the 4. Okay. So when I project this to the last coordinate, I obtain the measure mu. In fact, in any coordinate, I will recover the measure mu. So the projection you know what, let me phrase this as follows. So lambda of x cubed cross E is the measure of E, which is positive. So there's a positive probability that the point at random will be an Erdős square with last coordinate in E, which is one of the conditions we need. But now, as I said, the difficult part is to get that first coordinate to be equal to A. And so what we do, we need to disintegrate the measure lambda with respect to the projection onto the first coordinate. So idea, so we disintegrate lambda as an integral over the first coordinate of Dirac mass at, I don't have a good letter now, W, times some measure, okay, d mu of W. So I disintegrate lambda with respect to the first coordinate, and then I want to show that So that delta W times lambda W almost every point is an Erdős square. But not W, I want it for the specific point A that I start with. Because I really want Erdős square starting at A. So what can be done relatively easily, given what I've told you, is that for mu almost every W, this measure sees Erdős squares. But I don't care about almost every W, I care about A. And I really need to, because our correspondence principle cannot avoid that point. So if you ever dealt with disintegrations, this seems hopeless. You cannot disintegrate a measure and then look at it at a given point. So it turns out that in another stroke of luck, this disintegration turns out to be continuous. So these measures depend in the weak star topology continuously on the first coordinate. And the reason for that ultimately is because of this observation of host that I erased here, that you can always have this continuous factor map to the Kronecker factor. Okay, and because it's continuous, we can pinpoint the value at A, and then we can prove this statement, and that's how we finish the proof. So I think I'm out of time, so I'll stop here. Thank you.
Thank you very much for the beautiful talk. Any questions or comments?
Thanks for your talk. I have a question about the first theorem. So could we have a weaker condition that A contains infinitely many elements? About the first theorem, yeah, could we replace the condition with a weaker condition? Just A contains infinitely many elements.
Just infinitely many numbers?
Yeah, yes.
But A is infinite set, so it is that what you mean?
Yes, in this theorem, the density of A is positive.
Yeah.
So could we assume that it is zero?
Weaker assumption on A. No, definitely not. So I see. Yeah, so yeah, we can construct infinite sets that do not contain sumsets B plus C. There are some interesting sets with zero density, which we would like to contain sumsets B plus C, like the primes. This is a great example, but we don't know. Yeah, our theorem surely cannot answer that.
So your last theorem with Breina involved the sum of k infinite sets. Maybe a naive question, what about infinite sum of finite sets?
Infinite, no, so we cannot infinite, okay, we didn't think about this, but I would expect no. It maybe depends how exactly we're formulating it.
Well, infinite collection of sets of size 2 points. Each one is size 2.
Different sets.
Different sets of 2 points and you know, and infinitely many sets and all sums.
Okay, I didn't think about this, but yeah.
I mean, I haven't either. Just following your philosophy of going from finite to infinite, taking it one more step.
I think this is, yeah, I think this is easier. Yeah, I think we could do this.
Okay.
Any other questions? Okay, let's thank the speaker again.